All right, my friends, let's play with some macro data. We're going to look at interest rates, specifically the US 10-year Treasury. And what we're going to do is try to deal with the fact that we have some missing data. And then we're going to compute some sample statistics. Then we're going to compare that to a normal distribution. It's going to be fun. So what I want you to do is grab the 10-year Treasury, DGS 10. That's a daily government security 10-year maturity. We're going to go from January 2nd, 1962 forward. That's the first date they have available. I'm going to make that into a table so you can auto update. Then I want to create a double backfill. Now, if you haven't followed the other lessons, the double backfill is the notion that you're going to encounter missing data. Fine, maybe one particular day that's in a row for a date is missing. But what if there's two dates that are missing? We need to double backfill. The notion of a backfill is that if it's missing, look to the prior day. If two are missing, look to that day. No, look to that day. And then you fill in through. That's one of many potential approaches. In column D, what I want you to do, in addition to the double backfill, is deal with the issue that sometimes the table is going to go beyond what is the currently available information. We set it up that way to permit lots of auto updating features. So we'll use another conditional statement there, and then we'll compute the number of missing. So come on in. DGS 10, Lin, and D. You got the ticker, no transform, and daily. And I pulled this, I got data through September 29, 2025. Okay, so you get the value. I've already gone ahead and made this into a table. You remember how to do that, right? You're going to go ahead and highlight the region, insert table. Okay, so I already did that over here. So you would highlight all that stuff. And then every time that you type in a new column, like for example, you're going to go over here, type backfill, it appends that column, extends the table for you. So you have all the table features. All right, so Fred's giving you all that information. We want to do the double backfill. Again, you've seen a single backfill. Maybe you've seen the double backfill already. Let me make that bigger for you. There we go. Whenever you're dealing with these large if statements, the conditional statements, remember, go to the end. So what we want to do is grab the value. The value is right there in B7. So that column, the at representing that row where I am, which is row 11. That's what I want. Now, if what? There's a problem, meaning the value is not a number, is number at value equals false. So if there's a problem wherein there's not a particular value on that given day, then I want you to do something. I want you to give me B10, right? That's the one prior. I'm in B11. If that's not a value, then give me B10. But what if there's no value in B10? That's where the second conditional statement comes in. If is number B10 equals false. So if you have a problem there where B10 is not a number, then you're going to give me B9. So that's the way the double backfill work. Notice when you go all the way to the bottom, and hey, by the way, if you don't remember how to do that, on Windows, Control, down arrow, Control, up arrow, Control, down arrow, Control. So what we could do is actually count the number of missing values in each of those two columns. Go over here. We've named this DGS table, DGS10 table 3. We're going to pull the value column. And the count if is a similar cousin to the count ifs that we've used before. The S count ifs. The S just tells you you can include multiple criteria. We only need one if it is an A. Count it up, and there was 709 of them. Okay, well, we backfilled, so count if DGS 10 table 3 backfill. Now, the only thing that's different, watch. Look up at the top. Value, backfill. Value, look up at the top, backfill. So it's the same formula. If the backfill is missing, then count them up. All good. So I did a double backfill. Okay, scroll on over, take a peek again, go to Control Shift down arrow. There's a whole bunch of zeros. Go over here to date, Control Shift down arrow. You can see more carefully. Look, 415, 415, 000. Now, why are these 415? Remember the double backfill. If something is missing, something's not a number, then it's going to fill it in with whatever it was before. So that's dirty. I don't want all that. I want to clean it up. How do I clean it up? We've done that before as well. I want to put another conditional statement on this that's saying if the date is missing, then I don't want you to put anything. I want you to give me air quotes. So we're going to take this big old long beast and we're going to wrap that inside of another conditional statement. Can I get all that? Can I get, there we go, in one screen. So a lot of that should look familiar. In fact, from right here, if you could see my cursor, the if statement to the right is what we just had with the double backfill. I've added on the stuff to the left. If is number at date equals false, then air quotes. So in other words, in any given cell, row at symbol indicates that cell's row. The date, see it's at date, is not a number, is number equals false. Then give me air quotes. But if it is a number, then go ahead and do the double backfill we just did. And lo and behold, look at that. Nice and clean. That is not the only way to clean, but it is going to be advantageous for us, not only to view the table, but also to compute some sample stats. So let's do a little exercise where we're trying to find the first date, last date, and the observation value. So to find the first date, I want to run the min command. The minimum of the dates. Excel stores the dates as numbers, so you could use a numeric function like min. DGS10 table 3 is the table name, and we want to reference the date column. Now, if yours doesn't show up as a date, that's only because it's not set like a date. Excel reads the number. You are a human, not a machine, I think. Set it up as a date. So if we want the last date, just go ahead and click on the max. Now think about column M. Column M, you want the value on those dates. So I need to find that date in the table, whatever's the row in that date, and then call up the value associated with that row. That's a beautiful case for index match. The way that I read these is starting at the end. Okay, so match for me, L17. In other words, go to DGS 10 table 3. Look at the date column. See the where it says date. Find for me the date equal to whatever's in L17, which is the first one we just found through the min command. Now, the 0 just means get that for me exactly. Find me that row number. Now, index command is going to say, look in DGS 10 table 3, same table, the backfill column, and pull out whatever value in the backfill column is in that row. 4.06. Let's see if that's right. 4.06. Beautiful. Did the same thing over here for the last one. Scooch on over. And everything's set up except now we're referencing L18, which is the last date. Index and match, index and match. Now we want to compute some sample stats. Thankfully, we have some nice, pretty clean data. So we can just use our typical commands. Average on that table, brackets for the backfill column, standard deviation for the backfill column, mean plus 1, mean minus 1. You got the min, you got the max, you got the skew, you got the kurtosis. Think about what those things mean. What you have is, let's see if I can get that. Okay, so this is excess kurtosis. That means above and beyond 3. 3 is the magic number for the normal distribution. This is already extracting away from that 3. So this is actually 3.35. It's a little bit bigger, slightly fatter tail. So what we mean is there's likely more episodes out in the tails, more extreme episodes than you would see in a typical normal distribution. Slide over. If you haven't seen these before, the little red triangle on the top right means that there's a comment by little old me, right skewed, more extreme observations are greater than the mean. So kurtosis skewness together means there's probably some big stuff going on that's different than the mean. And if it happens, it's most likely going to be in this direction, leaning towards above that mean. Gains rather than losses, if you want to think of it like that, but it's really relative to the mean. Next up, maybe you haven't seen before quantile, but you definitely know the term percentile, right, from school. Are you in the top 10 percentile or whatever? Percent rank.inc. Don't worry about the INC. There's other options. This is just whether or not it's inclusive or exclusive. Don't worry about that. So percentile rank is going to find me the quantile, the percentile of M18. So what's M18? Take a look. It's highlighted. That's a beautiful thing when you click on the formulas inside of Excel. It is the value on the last date. The quantile of the last value, the quantile of 4.15. So it's looking at all of DGS Table 3 clean backfill. All right, so all of those 10 years and saying 4.15. Is it way down over here in the min? Is it way over there in the max? Percentiles or quantiles, the official thing. If it's 1, if that number turns out to be 1, that means that we are greater than everybody. We're the max, right? We're the biggest observation of all those interest rates that happen to be. That's if it was 1. What if it was 0? That means that we're the smallest. We're not bigger than anybody. If that was the quantile as 0, that interest rate, whatever it was the smallest in the data set. If it was 0.5 percentile rank, percent rank.inc came out to be 0.5, that means that whatever interest rate that spits out is 4.15 is greater than half of all of the interest rates that we've observed. The number is 0.306. So what that's saying is this number of 4.15 is approximately greater than 30% of the observations. 30% of the observations are less than that last value of 4.15. So it tells you a sense of how extreme it is. It's not quite in the middle of the distribution. And why is that? If you think about our sample statistics that we've talked about previously, and you see on the screen, the mean interest rate, the average interest rate on the 10-year Treasury is about 5.3. We're only now, scooch on, 4.15. So we're below the mean. We would expect it to be less than, around the 0.5 quantile. Okay, so what we just did was, if you think about your stats classes and you look at a CDF, right? What we just did was say, go along that horizontal axis, pick out an interest rate, and then go on up to the vertical axis. Tell me, what is the quantile level of that value? We can reverse it. And let's do this. So what we're going to do is pick out a whole bunch of different interest rates. Now, just pause for a second. Really, this should be quantile level. Not everybody uses that piece of jargon. I want to use that just to say that we're going to reverse it and we're going to make this a little bit different. So compute the quantile values for each of the quantile levels indicated in the table, compute the associated quantile values for a normal, and then compute on the density of the DSJ10. So these are hard-coded. I took each of the quantile levels, the 0th percentile or quantile, the first 0 percentile quantile, and so on all the way up to the top, the max, the biggest. Okay, so what I want to do first is say, okay, well, given that 0.01 quantile, that 0.01 percentile, what is the interest rate that's associated with it? Before we used percent rank, now we're using percentile. Percent rank went from the interest rate up to the vertical axis of our CDF. Now what we're doing is the reverse. We're saying, given a percentile level, a quantile level, what is the interest rate associated with that? Or if you want to speak in our parlance, for interest rates, when the interest rate was 0.86%, it was small. It was only greater than 1% of all of the history of the 10-year Treasury back to 1962. Meanwhile, percentile Inc., DGS 10 Table 3, clean backfill, K45. I don't know if you can hear that. Somebody's playing a saxophone. What we want to do here is say, okay, again, on that vertical axis of the CDF, pick the 0.3. 30% of the observations are less than or equal to what interest rate? The question mark is down on that horizontal axis of your cumulative distribution function, 4.11. Hey, take a look at this, okay? 0.3, 4.11, 4.15, 0.306. So what we just did was reverse the process. They're not exact because 4.15 isn't precisely at that empirical 0.3 quantile, but it's pretty darn close. So we reversed the process. Percentile Inc. again goes from given a percentile level on that vertical axis of the CDF, what is the value on the horizontal axis? The interest rate. Meanwhile, percentile rank is going the other way. Given an interest rate on that horizontal, what is the percentile level, quantile level on the horizontal axis? I wanted to do the same thing for a normal distribution in all of your stats training. You compare everything to the normal. Doesn't mean that it's right, but that's what we do. So let's use norm.inverse. So remember how we said we were reversing it? First we looked this way, we went down, and then we went this way, we looked up. We're reversing the process, norm.inverse, reverse. Norm just meaning the normal or Gaussian distribution. So there's a few pieces you need here. First, you need that probability level, the quantile level. In our case, 0.05 there. And then you need the mean, L23. And then you need standard deviation. That's L24. Now, think about it, right? If you're a normal distribution and you want to know who you are, what you look like, how you're shaped, all you need are those two things. All you need is the mean and the standard deviation. Because if you're normal distribution, no skewness, and kurtosis is magically set at 3. So for the actual data, empirical data percentile for the normal distribution, norm.inverse. A couple things I want to point out. Let's do that for the 0.01 quantile. It's the same formula. I locked in with the double dollar signs on the L and the row. L and the row for the mean and standard deviation respectively. So this looks all good, but look at the number. This is saying that given a series with a mean of 5.83 and a standard deviation 2.95, when you look at the probability distribution function and you go all the way over here to that left tail, where you go into small values, whatever is the quantile value such that it's bigger than 1% of the remaining values, that should be a negative number, minus 1.02. That's weird. That's trippy, right? Because what are we dealing with? We're dealing with interest rates. 10-year interest rates in the US economy, they don't go negative. They can. Short-term interest rates, you can think about going negative. They went negative in Europe. There's several cases, but they typically don't. So this is a situation where we're learning about stats. We're taught the normal distribution. We apply the distribution to everything, but it's not relevant here. We have a zero lower bound, right? Effectively a zero lower bound on this profile. So what we have is in our distribution, actually, our lowest scores, our lowest instruments, our lowest interest rates are shifted over. If it was a normal distribution, we would expect them to be negative. They're actually positive. This is simply how much more positive, subtracting the two. So our left tail is shifted over. It's thinner than what we would expect if we had a normal distribution. In the particular area of the curve that we were playing with, the quantile level of 0.3, where the data said it was 4.11. If this was a normal distribution, what that mean with that standard deviation, we would expect 4.28, pretty close. The negative sign means that what we have is, look at the subtraction, The data is a little bit less than where the normal distribution would say. But, on target. Now, go further down into the other tail. And let's go all the way to like over here. Subtracting the two. This column L, remember, is our data's quantile value, 14.04, and the normal distribution, 12. So when you go all the way to the right, when you get those big values, we're saying that when I get to the big values of the 99th percentile, 99 quantile, meaning that we're bigger than just about everybody, only 1% is bigger than us, our data is at all the way at 14.4. But if this was a normal distribution, it would only be 12.68. So we have more extreme interest rates on the upside and less on the downside, which makes sense given the fact that normal distribution isn't appropriate given that truncated left tail, that zero lower bound, as we talked about. Last thing I wanted to show you was what this looks like historically. So I have a dynamic title set up where I use the concatenate command, where I physically wrote in quotes 10-year Treasury yield. And then I converted the L17 and L18 into text values, L17 and L18. L17, L18, first and last date. So the concat allows me to create that string. In my chart, then, I reference that string, that cell. So every time I update my data, that will update as well. You have the 10-year Treasury in blue. I have 3 hash lines. You don't need to do this, but what I like to do is call attention to the most recent value. So I set the red line at the most recent value. And then I have 2 green lines at the 10th and 90th quantiles. How do you get that? Over here, the last value I'm referencing M18. Q90, I'm referencing L57 from the table that we made. And the Q10, I'm referencing L41 from that quantile we just made. Scooch on down, and that gives me a sense of where we are, red line, relative to where we typically are, the 2 green lines. You don't have to do 10 and 90. You could do 25 and 75. Sometimes that's called the IQR, interquartile range. All right. Hope that helps.